So there is a derivation. So I'll just explain. Uh, in the previous video, I told about impulse train and how do you represent it in an equation. So this is how an impulse train is represented as an equation. Okay. Now since this train is periodic with Ts, whenever it's periodic, we can represent it using Fourier series. So what's there is a formula for Fourier series, and that is this. It goes like this, where dn will be 1 by ts minus ts by 2 ts 2 delta of ts e power minus j 2 by n t by ts dt. Okay, so this is the formula, and this is the formula for dn, and I find that dn will be I by ts. Okay, so I will substitute I by ts here. So when I substitute I by ts and I take it out, it will be delta ts of t will be I by ts from n is equal to minus infinity to infinity e power j 2 pi n t by ts. Okay, so now this is done for the impulse train. We know that ms of t is what m of t into ts of t. This we know from the previous video that I explained. Uh, Now I got this right, delta of ts of t. Now I'll substitute this in this. So it will be what? M of t I of ts n is equal to minus infinity to infinity e power j 2 pi n t by ts. And this will be I by ts m of t. I've taken this out and I've taken this inside. And if I expand this, I'm expanding it for, let's start from uh, some point. Now if I expand it from some infinity point, I, at some point it will come to 0, right? At 0 this n will be 0, so it will this whole terms becomes 1. So this there will be no this term, so it will become m of t at some particular point, and so on. If you go on expanding it, this will be, since n can be minus 1, it will be minus here. uh, Here I'm not substituted for n, let it be n because I know it is some negative value, and here I have substituted n is equal to 1. When n is equal to 1, it will be e power j 2 pi t by ts, and so on. Okay, so this is my expanded version. So what I did till now is I know the equation for my impulse train, I know the formula for my Fourier series, and I found an equation for delta of ts of t, and that I'll substitute in this formula. That is the reconstructed message signal. And when I substitute it and I expand it, I'll get this. Now I want it to be in the frequency domain. Now in the frequency domain, what happens is this term, whatever is like, let me take an example and explain. Like if there is a term like this, And when I convert it to an um, for frequency domain, what happens is this m of t becomes m of f, and here 1 by ts. So this can be basically represented as fs. 1 by ts is what f is. So it will be m of t e power minus j 2 pi fs. This can be basically, and if there is an k here, this can basically be converted into m of f plus kfs. So whatever term is there here, and if there is a minus here, it will become plus m of f plus kf of s. If it was m of t e power minus plus j 2 pi just fs, there was no k, then it will become m of f plus fs. Sorry, it is plus here, so it would have become f minus fs. So this is how you convert from shit. This is if there was m of t, and if there is an e power minus j 2 pi kt by ts, I can convert it into m of t e power minus j 2 pi kfs. Uh, and if there is a minus sign, there will be an plus here in the frequency domain, so it will be m of f plus whatever term except for j 2 pi, that kfs. And same here, if there is an plus sign instead of minus in the frequency domain, it will be m of f minus fs. So this is how it works in the frequency domain. So to revise again, I have an impulse train. I have represented it in an equation. I know Fourier series of it. I found the equation for delta of t of s, and then I substituted for it in the message signal formula, and after that I got an equation in time domain, and then I converted it into frequency domain. And after converting it into frequency domain, this is what I'll get. And so on, that m of f plus fs plus m of f plus m of f minus fs, and so on. See, in the first, in the at the time is equal to 0, I'll get m of f, and this side I'll get minus fs, and the other side, on the left hand side, I'll get plus fs till kfs, and here till minus kfs. So this is what I got. So if you want to show exactly how the transformation happens, then you can use the formula for Fourier transform and show it. So for example, if this is a formula, and this is the time domain formula. So I want Fourier transform of what? I wanted Fourier transform of m of t e power minus j 2 pi fs. So this whole thing, I will substitute here. But I wanted m of f, right? So I substituted in that m of t e power minus j 2 pi fs ft t. So Fourier transform of that will be uh, this will be minus j 2 pi ft t. Here it will be fs, right? Because if it is fs. So if I join both of these terms, then I'll get it as minus j 2 pi f plus fs of t dt. Because these terms can be added in the power, and when you add it, this term j 2 pi will be common, t will be common, f plus fs will remain. So whatever terms comes here, that will be your Fourier transform. That it will become m of f plus fs. Because look at this formula and compare here. So whatever was f, that was here. So in the end, I got it as f f plus fs, so it will be m f of f plus fs. So this is how this is a mathematical way of showing what exactly is happening when you reconstruct an wave. So you got an formula for this. So let us look at the waveforms. So these are the waveforms. So let us assume this is m of f which has a bandwidth of uh, 2 fm. Like, you don't consider it as 2 fm actually, because you consider bandwidth only for positive side, so it is basically fm. um, Now we know that from sampling theorem that fs should be always greater than 2 fm. Now let us check for three conditions. When fs is equal to greater than 2 fm, fs is equal to 2 fm, and fs is less than 2 fm. So when fs is greater than 2 fm, this is the waveform that you get. So when you get this waveform, I can take this out. Like, I want this particular signal. I've reconstructed it and I want only this part. So I can basically put an filter here and I can just extract this part, right? So it is easy here. Now when I come to fs of 2 fm, uh, the waves will be joined. Like, one wave ends here, the other wave starts at the same position. Here there was a gap, so I can easily extract it, and there was no overlap or something. But here also you can extract it, but there are chances that some distortions will creep in. And then when fs is less than 2 fm, this is what happens: the signals overlap. Here it is ending at FM, but the other signal is starting at somewhere less than FM. So the reconstruction is not possible, because if you try to reconstruct using a filter over this part will be extra, because this part is overlapping and there will be distortions. This particular part where it is overlapping is called area of distortion. So that was it for the spectrum of ms of f.